Hey, yo, what's up, guys? Baby Bear 4812 coming at you one more time. The delete node in a BST problem is the one we're working on today. It's 450. It's an oldie but a goodie, and Microsoft, Bloomberg, and Cisco like it. I haven't heard of Cisco in a while. It's a pretty classic problem, and I think off the bat, like right off the bat, it seems a bit tricky, and it's not always it's not the most intuitive thing to think about. So I think it's a good problem. I will throw the caveat out there. There are two ways to solve it, depending on how you interpret the instructions and or how they're given to you, maybe in an interview. So I'll mention both methods. I'll only be proceeding with one of them, but that's just a caveat before we jump in. So if we read the description, we're told that we're given a root node reference of a BST and a key. Sorry, a BST and a key. Delete the node with the given key in the BST. Return the node reference, possibly updated, of the BST. So what does that mean? It says basically the deletion can be divided into two stages. Search for node to remove. If the node is found, delete the node. Can you solve it with time complexity O of height of tree? Yes, we can and we will. And so what they're referring to is this is if we're given a reference to this root node, for instance, 5, and the key we're told is 3, meaning key is what we want to remove. Let's return this tree as it is with 3 gone, and in its place we might need to shift things around to put them where they need to be. In this case, we take the 4 and we move it up over here instead of the 3. I will also add another valid solution is if you brought the 2 over and moved it up into 3 spot. And remember, we're dealing with a binary search tree here. And whenever you're in doubt or whenever you get these questions, I'd always boil things down back to first principles. Binary search tree means every parent has up to 2 children. The left child is always smaller than the parent. The right child is always greater than the parent. So everything in the right subtree is greater than your current value, and everything in the left subtree is lesser than your current value. Okay? We get something like this where key is 0. 0 is not in here. We don't end up deleting anything. That's fine. And if we're given an empty root, we return nothing. So that's some basic error checking. Okay. So let's talk about how we're going to approach this problem. So I mentioned my piece on kind of the first principles. Let's look at this example here first. Move myself up a bit here so I'm not in the way. As always, my pen's gone. Where is it? Cool. Let's say I wanted to remove this 3. Okay? I'm given this tree and I'm told I need to get rid of 3. The way that we're going to do this in O of H height is basically by abusing the fact that this is a binary search tree. If I'm told that the key I need to get rid of is 3, okay, I start at 5 and I'm told I need to get rid of 3. Where am I going to do my searching? In my left subtree right here or in my right subtree? Well, 3 is less than 5, meaning that we're going to jump straight into here. Whatever's on the right side of 5, or for you guys, I guess the right side of 5, irrelevant. We don't care. It's all greater than 5. It is not 3. We're not going to be doing any rearranging there. And so by doing that repeatedly, obviously in a recursive manner, which I think it's obvious that this question calls for that, that's how we will go about doing this in O of H time, right? So I take a step here. I compare. I'm going to start by comparing the value I want to the value I'm at. I say I need to get to 3. 3 is less than 5, so I'm going to take a step to the left. Cool. So far, so good. Then we get here and we realize, okay, well, now maybe this is more appropriate. Now I'm looking at the 3. Okay, damn, this is the value that I want to get rid of. Well, now here's where I was mentioning earlier about the 2 approaches. And this is something you want to bring up and discuss with your interviewer and ask them how they would like you to proceed. There are 2 ways to interpret this problem. One is to acknowledge the fact that this node is a reference in memory. Okay? This node is a unique reference in memory. So what I can potentially do is to say if I want to get the 4 in here, and again, I'll talk about how to get there, I can just say I'm going to change this value to the 4. So not the actual node, the reference in memory will stay there, but the value will change. I will then go ahead and change the value of this to be none. What we've done in this solution is we've actually set, and obviously this cuts off this connection here. What we've said is that we're actually returning a tree that looks like how we want it to look. However, the references in memory have stayed the same. This node here, which was originally a 3, The 5, 5 dot left, if you will, still points to that same spot in memory, that same reference in memory. If your interviewer is cool with you moving the values around and not deleting or removing this reference in memory, then that's good, then we can do that. Otherwise, you got to take a separate approach of saying, let me figure out how to actually get rid of this and move this pointer kind of over here, and then potentially make like this 2 point into here, and move a few things around. I'm making it sound a bit more complicated than it is. It's doable. I might make a separate video on that. But the approach that I'm gonna be doing here is actually taking this value, changing it to something else, and then almost in a cascading effect, all the rest of the values that are going to be changed will change those sequentially as we go down. All right. So those are the two different approaches. One is actually shifting around the pointers to point to different spots in memories where the nodes exist, or the one we're going to be doing is to leave the references in memory where they are and simply change the values in those references so they look like the binary tree that we want them to look like. All right. The answer is I don't know if one approach is more appropriate than the other, if it's more correct. I've seen discussions online arguing for both. It's for greater minds than mine to figure out, but like I said, I'm just going to be walking through one way of doing it. Now, one thing that I said earlier was, I don't know why my pen is gone now. One thing that we wanted to do earlier was to say, okay, 3 we need to get rid of. Now the question becomes, what do we replace it with? Well, if we replace it with either the 2 or the 4, remember that both of those are smaller than the 5. So as long as we're dealing within this domain, that rule will be taken care of. Everything to the left-hand side will still be smaller than whatever parent we're at. So we're good. The thing is though, and I've drawn a second example here to make this a bit more clear, we need to make a decision. We need to make a decision if we go with the 2 or we go with the 4. If we go with the 2, that'll work just fine because this will become a 2. And it just so happens that everything to the right of the 2 is greater than the 2. This now becomes none, so we're safe here as well. Conversely, if I go with the scratching this out and I make this a 4, everything to the left of the 4 is smaller than it, and this is a none, so we're safe here as well. This becomes a bit less obvious if we go down to this example. And I'm looking at this bigger tree now, and I say, let me get rid of the 5. Okay? Oh, sorry, I'm getting rid of the 5. Well, if I pick the 2, say I get the 2 up here, then does this work? Well, now on the left-hand side of the 2, we've got the 1 and the 4, okay, but, sorry, I've confused myself here for a second. If I take, for example, if I just arbitrarily pick the 2 and I say, okay, this is going to become 2, and then what is this going to become? Well, if this becomes a 1, then the 4 is greater than the 1, sure, but 4 is greater than 2 now, and that's not good because everything to the left of the 2 should be smaller. So that's not really an option. So you say, okay, maybe I'll put the 4 here instead. So if we put the 4 here, it's like, cool, but wait, like 4 is greater than 2, how can it be on its left side? So this isn't going to work. We can't put the 2 there, so how do we decide? We try the similar thought experiment with the 7. Say I put a 7 here. And then the 7's got to be replaced with either a 6 or an 8. Well, if I put the 6 here, wait, 6 is less than 7. It can't be to its right, so that doesn't work. If I try to replace it with the 8, okay, that works. So the 8 works. Why did the 8 work, but the 6 didn't? Right? And similarly here, the 2 didn't work, but what if I try one of these numbers? The key is this. If I move something up from the left-hand side, okay, if I move something here from the left-hand side, it better be the maximum of my left-hand side. If I move the 4 up here, and this becomes a none, this works because the 4 was the maximum value on the left-hand side. Everything to the left of the 4, which is all this stuff, must be smaller than it. So I can take the maximum of my left subtree and replace it here. So this can be max of left subtree. However, we said as well that the 8 works. So, sorry, did we say the 8 works? I think I messed that up. Sorry, I wanted to say the 6 works, so the 8 would not work here. If we had the 8 here, if we put an 8 here, well, the 7 is smaller than the 8, and so is the 6, but both of these are on its right-hand side. So if it's smaller than this value, we can't have it to the right. meaning that the only thing I could replace this with would be the 6 here. The reason I could replace it with the 6 is because 6 is the minimum value in this entire right subtree. If I take the minimum of the right subtree and I put it up here, so this becomes a 6, this becomes a none. Everything to the right of it is greater because by definition the 6 was the minimum in that side. That leaves me with the decision then that I could take either the max of the left subtree or the minimum of the right subtree. Right? Either one of these will do, and that's the decision that we're going to make. No matter which way you skin the cat, you'll end up with the exact same result, and you'll end up with the same kind of logical decision to make. In that, if you need to replace this value, you need to do it with either the maximum of its left subtree or the minimum of its right subtree. Now, even greater, I'm going to even take a step back here for a second. This is one of the cases where we are replacing a node that actually has children. Okay, and maybe I should have even said this earlier, but if we need to get rid of a node, like let's say we were told we wanted to get rid of the 4. If we need to get rid of the 4, cool, find 4, set it to none, it has no children, done. If it has no children, it becomes trivial. It's a leaf node. We set its value to none, and we're done and dusted. Ain't nothing to it, okay? If it does have a child, however, then we need to make one of these decisions. A lot of the explanations you'll see online will tell you that, there are 3 cases. One is no children, the leaf node, that's trivial. 1 child, or 2 children. I'm going to treat whether you have 1 or 2 children the same. We're pretty much going to be making the same decision. Depending on if you have a left or right child, it might be slightly, like you'll have to pick either the max of the left or the minimum of the right. But regardless of that, it'll kind of fall under one bigger case. And so I hope that explanation made sense. Let me know in the comments down below if I need to clarify any points. This is by and large, this covers pretty much all the logic we're going to need, and the code isn't going to be very long. So I think we're in a good position where you can jump in, try to code this thing out, and see where we get. Maybe at this point I'll move my face back down. There we go. So we can begin by doing some standard error checking, like usual. So I'll say if we're not given a root, then we're just going to return none. And then let's think about the following. So with this delete node function, we're going to do a recursive call on the function itself. Since all we're passing in is the root and the key, we don't need to really be we're not going to need any other information that exists outside of these 2 data. And so no matter what we do, whatever manipulations we make, at the end of the day, I think I'm just going to return the root. This is going to anchor me down at the bottom, and now I can kind of think to myself, what are the different cases in my actual recursive relationships here? So we can jump into the recursive relationship now, which is essentially going to tell us when we're going to make a recursive call on this function. We're going to make a recursive call on this function if we have not yet gotten to the key that we want to replace. So our first scenario is if the key is less than the root value, meaning we want to search the left subtree. Okay, we haven't gotten there yet. We're sitting at a 5. We want to get to 3. I'll give us a bit more space. If this is the case, and since we're returning root at the bottom here, I'm going to want to set my left root value to be whatever the result is of this recursive call on delete node. And so we're going to call it on root.left. So we're going to look at the left subtree, and we're going to pass in the same key. Otherwise, if the key is greater than the root value, so again, we still haven't found it yet, I'm going to set my right root to be equal to the result of this recursive call in the delete node function. We're going to call it on the right subtree, and we're going to pass in the same key. Otherwise, this otherwise means we've actually found the root that we wanted to find. And if this is the case, then we need to see whether or not we actually have found a leaf node or we have children that we need to deal with. If I found a leaf node, namely, if not root.left and not root.right, so both of those are none or null, then I can just say, root.val is equal to none. Or even better yet, we can just say root is equal to none. What this is going to do is this is just going to say, well, we found a leaf node. So we found, for example, I'm trying to get rid of this 4, let's say. Well, 4 doesn't have any children, and we want to get rid of it, so just set it to none, and we're done. Eventually, we're going to return that, and if we were, for example, if we were sitting at this 2, let's say we're sitting at the 2, we wanted to get to the 4, all right? So I'm sitting at the 2 and I say my key is greater than my root val. This will put us into this recursive call, okay? And we're gonna set root.right to be whatever is returned from that call. That call is going to get us to the 4. We get to the 4, that puts us in this case. We're gonna set the 4, which is in this case root now, to none, and then we're gonna return the root, meaning that root.right is going to be none. All right, that's how we're dealing with that. Now, I'm gonna say the following. Otherwise, if this isn't the case, it means we have 1 or 2 children. Otherwise, let's say we actually have a right child. Okay, then we're gonna do something. Otherwise, and maybe just make it clear, I'll say if root.right, and again, I'm putting pastor just as a placeholder. This is going to tell us like, we may have one, we definitely don't have 0 children, so one of these exists. If it just so happens that the left child exists, what I'm gonna do is I'm gonna say, get the max of the left subtree. If the right exists, I'm going to say, so if the left doesn't exist and then the right does, I'm gonna say get the min of the right subtree. If I wanna get the minimum of this left subtree now, if I wanna get the maximum of the left subtree, that's going to replace the current value of the root that I'm at. So if I'm sitting at the 5 and I wanna, I've got this subtree and I wanna replace it with the maximum of the left subtree, so I wanna replace it with the 4. That means that I'm going to want to do the following. I'm going to want to set my root.val to equal, we'll say something like get max left subtree, okay? And we're going to call that on root.left. I'm then going to say take my actual left subtree, so root.left, and we're now going to need to do that cascading, so recursively set its value down to where we want it to be. So we're here going to, once again, call delete node. We're going to call it on the left subtree, and the value that we're going to want to delete is going to be this root.val. So if I've set, I want to change the 5 to a 4, okay? I've changed this value here. My root.val is no longer 5, it's 4. I now want to go to my left subtree and delete the root, or the node, whose value is 4. So I want to go down and delete this thing, and this thing will now become none eventually. I now want to delete the 4 because I've gotten rid of the 5. Otherwise, I'll have a 4 here where the 5 was, then I'll have another 4 here. That's why we want to do this recursive call. I'm going to do the same thing here, and I will write this function up, by the way. So I'll define those, and they'll be very quick to define. We're going to do the same thing here. We'll say root.val is equal to self.get. In this case, I'll write a different function called get min of right subtree, and I'll call that on root.right. And then we'll say root.right is equal to self.delete node, and we're going to call this on the right side. And again, we're passing in a root.val for the same logic that I described above. I think I'm going to move this a bit more over so I'm not hovering over the code. If I want to define get max left subtree, and I'll do self, and we're going to have some root, okay? I'm passing in root.left. So I just want to find the maximum of whatever this subtree is, meaning if I want to find the maximum, I want to keep searching right. So I'm going to say while root.right, root is equal to root.right. This will keep traversing me down, and I'll eventually return the root, okay? Actually, since I want to set my value here, I'm going to return root.val. Something super similar for get min of right subtree. Self and root is what I'm going to pass in. I'm then going to say while root.left. Since I want to get the minimum, I want to keep traversing leftwards until I get to the smallest value. I'm going to say root is equal to root.left. That'll keep, shoving me over, and then I'll return root.val. This is going to assign the value, this is going to assign the value we want, and then it'll delete that subsequent value that we took. That's why we're passing this root.val here. I'm gonna run this super quickly just to make sure that I didn't make any typos or other logical mistakes. Let me submit this, and we're good. Cool. So let me show you guys the code again. You see it all here. To summarize it all, there are 2 ways of doing this. I don't know why I keep doing this every time I say 2. 2 ways of doing this. One is to actually change the references in memory, or rather where the pointers point to in memory, and the others was to adjust the values like we did. Clarify with your interviewer which one they want. I went with this approach. I think it was a bit more intuitive. And after we decided on that approach, we said we kind of acknowledged the fact that everything to the left of my root is smaller than me, everything to my right is bigger than it. So we made our recursive calls depending on whether we're going to go left or right, depending on the value of where we were at compared to the key. Okay. Once we actually got to where we wanted to be, we then said, if I don't have any children, just set me to none. Otherwise, if I have a left child, grab me the biggest thing out of my left subtree, set my value to that, and then get rid of that subsequent piece afterwards, the one that we copied over, and then same thing on the right hand side. I hope that made sense. Let me know in the comments down below if you have any other questions, any other comments, or any other questions you want me to solve. And that's it for now. Hope you guys enjoyed, and I'll see you next time. Peace.